Okay, so we had several questions in our office hours regarding the Unit 6 Module 1 pop quiz and the homework. So I'm going to work out several of the questions that were asked during the office hour. Okay, so the first question is about ibuprofen and how it reacts with water and what we expect to form. All right, so the first thing we want to recognize is that the carboxylate group in ibuprofen, that's the COOH that's circled, will undergo a reaction that generically looks like this. You have some amount of carbons, some amount of hydrogens, and some amount of oxygens. It'll react with water. Now, carbon and oxygen isn't going to change, but the number of hydrogen atoms is going to decrease by 1. And that's because the molecule is going to donate a hydrogen, H plus, and it's going to take on a negative charge. And all acids do this. They all donate an H plus and change charge. And they produce H3O plus in water if reacting with water. Okay, so the general idea is that the molecule, the acid, reacts with water, donating an H plus, takes on a negative 1 charge, there's 1 less hydrogen, and the water gains it and turns into hydronium. All right, for this reaction, we have C13, H18O2 plus water. We'll make C13, H17O2 minus charge plus hydronium. And that gives us the top option. In this question, they say how many of these drugs act as an acid in water? And in this case, water would act as a base. So we look through the molecules here. We want to identify functionality, acids. All right, in the acids summary, acids in Unit 6, Module 1 are COOH, or a positively charged nitrogen, positive charge with 4 bonds to the nitrogen. All right, so that means Solendac has this group, phenylprofen has this group, but orphanedrine does not. It has a neutral nitrogen. It needs to be a positively charged nitrogen to be an acid. That would give us answer D. Select the chemical equation and type Ka or Kb that represents the reaction of lidocaine with water. Okay, so then we have our first base analysis. Now this one has 2 to choose from, but either one is fine. What we see is that bases plus water, right? That means now the base takes on a H plus. It gains an H and a positive charge. The result is water has now lost an H plus and becomes hydroxide ion. If we look at the generic reaction, CXHYOZ N2 or N2 plus water, we would take on a hydrogen, so we get H plus, where we're taking on H plus and an overall charge of plus 1, and then so we gain the H plus, and water lost an H plus and becomes hydroxide ion, negatively charged. So when we take a look at the different products here, we need to choose the 2 that have H23. And now the question is to choose between A and C. It's whether the reaction is Ka or Kb. And in this case, because we're producing hydroxide ion, we know we have a Kb reaction. So Kb, the equilibrium constant Kb, always produces a hydroxide ion. Ka, always the products include H3O plus. So that's one of the ways to remember, is it Ka or Kb? The question is, okay, well, what's the product? Is the product hydroxide? Then it's Kb. The product is hydronium. It's Ka. All right, so we're given a reaction. The reaction has a hydroxide ion. So that means we're undergoing Kb. Now we have the same type of table for Ka, pKa, so let's just fill it in. pKa plus pKb is 14, that's on top. And if you want to go between Kb and pKb, these are the two equations depending on what you're given. If you're given Kb, then you could take minus log and get pKb. If you're given pKb, then you can determine Kb. On the other side, we have the same two reactions for pKa and Ka, and then the relationship between Ka and Kb. If you needed to cross over, if you're given Ka and you need to find Kb directly, then you can use the bottom equation. Okay, so with that, we're given pKb, and now we're asked for Kb. So we can use these equations. 10 to the minus pKb is Kb. 10 to the minus 9.13 is 7.4 times 10 to the 10. In this reaction, we are asked to identify all of the species that act as acids. So 2 of them are going to act as acids, 2 are going to act as products. So we recognize acids in a couple ways. First, they donate an H+. Right, so all positive charges are acids, right? That's one of the quick way to do it. All negative charges are bases. Neutrals depends, right? You have to really take a look at the functionality of each group if they're neutral. If it's C double bond OH neutral, that's an acid. If it's neutral nitrogen, that's a base. Water can act as an acid, and we would know that if the products involve hydroxide ion. Water can act as an acid, as a base, and we would know that if the products are H3O+. So that's sort of the story behind neutrals and charges. And now when we look here, we see hydroxide ion, we see a positive charge. So the positive charge here is an acid. We know hydroxide ion is a base. That also means that the conjugate on the other side of the reaction must function the other way. So water must be acting as an acid here. And the conjugate of the C18H19NOS must be the base. And it's a neutral nitrogen, so we can also get it from there. All right, so this is the most often asked question in office hours, so I'm going to go through it the way we did in the office hours. So let's take a look. So the first thing we want to do is start by thinking about organizing our acid strengths. So the acid strengths kind of look like this. The lower the pKa is, the stronger the acid. So I'm going to put the lowest pKa, strongest on the bottom, and the higher the pKa is, the weaker the acid. And that's because Ka is 10 to the minus pKa, so pKa is 10, and Ka is 10 to the minus 10, so it's very weak. Okay, so what we could also need to do is organize the conjugate base story. So the conjugate base story goes in this way. The strongest, right, the strongest conjugate base has the weakest acid. And the weakest conjugate base has the strongest acid. So if you're looking for a value that does scale, or a property that does scale with pKa, meaning the lower it is, the weaker it is, the higher it is, the stronger it is, that occurs in the conjugate base side. So if we rank these, we see Tylenol is the weakest acid at 10 to the 9, pKa of 9. The strongest acid is aspirin at 3.5. So the lower the pKa, the stronger the acid. So this also means that the strongest conjugate base is Tylenol, and the weakest conjugate base is aspirin. So now that we have this structure, we can kind of go through now each of the options. It'll be easier to analyze. The first one says the conjugate base of Tylenol is stronger than the conjugate base of ibuprofen. And that's true. Tylenol is as the top is the strongest conjugate base, and it's going to be stronger than either ibuprofen or aspirin's conjugate. Tylenol, strongest conjugate. Okay, next. Ibuprofen is a weaker acid than Tylenol. And that's not true. Ibuprofen is stronger as an acid than Tylenol. Ibuprofen's pKa is much lower than Tylenol, so we would expect ibuprofen to be a stronger acid than Tylenol. The conjugate base of aspirin is stronger than the conjugate base of ibuprofen. That's wrong. Aspirin has the weakest conjugate base because it's the strongest acid. So we can see that in our ranking. So aspirin is the weakest conjugate base. There's no way it's stronger than anything else in this table. Aspirin is a stronger acid than Tylenol. And yes, that's correct. We know aspirin is the strongest acid. It's got the lowest pKa, and so it would be the strongest of the acids shown here, and there would be the two correct answers. So organizing the strength of acid and its conjugates in this way really help in this problem. All right, this is a computational problem, so let's set it up. So we know that the product of hydronium times hydroxide in water must always be 10 to the minus 14. So when we're looking at water at pH 7, so 10 to the minus 7 molar hydronium, 10 to the minus 7 molar of hydroxide. That's neutral water, so their product is 10 to the minus 14. Now we're being told that the hydronium concentration is 10 to the minus 5. And what that's going to do is drive down the hydroxide ion concentration. So we know that we can find the concentration of hydroxide by taking 10 to the minus 14 divided by 4.2 times 10 to the minus 5, and we get 2.3 times 10 to the minus 10. So that product, 4.2 times 10 to the minus 5 times 2.3 times 10 to the minus 10, is going to be 10 to the minus 14. Right? All these, at every combination of hydronium and hydroxide that's allowed, their product must always be 10 to the minus 14. So this leads to relationship. As hydronium ion goes up, if it's greater than 10 to the minus 7 molar, then hydroxide ion must be less than 10 to the minus 7 molar. And we also see this with the pH and the pOH. If we take the minus log of both values, so the pH here would be 4.3. The minus log of 4.2 times 10 to the minus 10 is 4.3. And that gives us a pOH of 9.6. We can either get that value from taking 14 minus 4.3 or taking the minus log of 2.3 times 10 to the minus 10. Okay, so here we have a panel of molecules, and we're asked which one is going to produce a basic solution, or which one will increase the number of hydroxide ions. So to increase the number of hydroxide ions, we must undergo Kb. Why is that? Because Kb's products always produce hydroxide ion. So any neutral nitrogen reacting with water will produce hydroxide ion and its conjugate base. So this will always make hydroxide ion go up. The other substance we can put in water that would create hydroxide ion is the conjugate base of a carboxylic acid. So COO minus will act as a base, and so it will regenerate its acid, its conjugate acid, plus hydroxide ion. So either one of these would do it, but we see through the panel that we don't see the COO minus, that's not present. So we have to focus on the neutral nitrogen groups, And we see that the neutral nitrogens will produce, there are two of them. The third one will not produce the hydroxide ion. Instead, it will increase hydronium ion, reducing the hydroxide ion concentration. So the third one will do the exact opposite of what we're being asked about. Okay, so in this problem we asked about problem A. So problem A has a neutral nitrogen, Kb. So we know by our formula that the number of hydrogens must increase. Whoops, whoa. Sorry about that. The neutral nitrogens must decrease. So in this case, the hydrogens must increase with the positive charge, creating hydroxide ion. This is Kb. And so for this formula, C5H8NCl, we are going to go to C5 plus C5H9NCl plus hydroxide ion. And that also means that the only product here can be B, the one that's correct. You must gain a hydrogen and it must go to hydroxide ion. Item D must never be selected, right? It's often selected on tests incorrectly. That would be Ka, but neutral nitrogens do not undergo Ka in water. All right, so let's make a summary of everything we've talked about. Acids in water produce hydronium. pH goes down. Water acts as a base, and it makes H3O plus as a product. They form their conjugate bases as products. If they're strong acids, there's only three of them, HCl, HNO3, and H2SO4. All the others are weak, and the two that we've spoken about are C, double bond, OH, and NH. Any nitrogen with a positive charge, so any molecule with a positive charge will act acidic, but the neutral will be COOH. So for bases, we have a similar summary. In water, they make hydroxide ions go up. They make the pH go up, become more basic than 7. Water acts as an acid, and by doing so, it makes its conjugate base hydroxide ion. They always form their conjugate acids. The strong bases are the metallic hydroxides. You put those in water, you only get hydroxide ion. The weak bases are all neutral nitrogens with a lone pair, and all negatively charged oxygen atoms are also weak bases. All right, so that's our summary. This is everything we talked about in office hours that students had questions on when they were either doing their homework or doing their pop quiz. I really encourage you to work out each of these problems before we start Unit 6, Module 2, when we return on after break.